Hello, this is a continuation of tutorials or workthroughs of the 93202 2024 NZQA Scholarship Calculus examination. I've already posted videos on questions 1 and 2 from the 2024 examination, so this video will cover question 3. Some interesting questions in question 3. So let's move on and see what we've got. So here's the first question. It says find the exact value of the integral from 0 to 2 pi of cos 2x over cos squared x dx. And when a question says exact value, what they mean is not a rounded value that's been plugged into your calculator. So if you get pi's or e's or square roots, you can leave them in that form. So the technique that we use for this question is that we have some expressions for cosine 2x. The basic one, not sine, it's usually cosine squared x minus sine squared x. So we can change this into cosine squared minus sine squared. You can also change it using cos squared plus sine squared equals 1. You can change this into cos squared minus 1 minus cos squared x, which is cos squared minus 1 and minus minus plus, so 2 cosine squared x minus 1. Or if you write cosine as 1 minus sine squared, now you get 1 minus 2 sine squared x. So we've got effectively these 4 expressions that are all the same value, and that will help us do this integration. So let's just write it out. The integral from 0 to pi over 4 cos 2x over cos squared x. Because I've got a cos squared in the bottom, I think, well, actually any of these 3 would probably do. I'll do it 2 of the ways. If we use the first one, this is the same as the integral of from 0 to pi over 4 of cos squared x minus sine squared x over cos squared x. Cos squared over cos squared is just 1, and sine over cosine is tangent. Now we can integrate 1 easily, but tan squared we can't. We can use another identity. We used above, we used sine squared plus cosine squared is equal to 1. If you divide this through by sine squared or by cosine squared, you get 2 other identities. So dividing by cosine squared, sine over cosine is tangent, so you get tangent squared x. Cosine divided by cosine is 1. 1 over cosine is sec, so sec squared x. This is the one we want to use here, so we can replace this tan by sec squared minus 1. These Pythagorean identities, they come just from a right angle triangle. If you've got 1 on the hypotenuse, you would have sine x here and cosine x here, right angle. And that's where the identities come from. If you divide this by sine squared, you get 1 first. Cos over sine is cotangent. Oops, try to write. And 1 over sine is cosec. So there's 3 identities that come up a lot and are very useful. So back to our integration. we've got the integral from 0 to pi over 4 of 1 minus, and tangent we said was secant squared minus 1. So secant squared x minus 1 dx, that's 1 minus minus, so it's 2 minus sec squared x. And the advantage is that sec squared x is a standard integral. Tan x differentiator gives sec squared. Going back the other way, you'll just get tan x. So we get here, integrate 2, you get 2x. Integrate sec squared, you get tan x. And this is evaluated at 0 and pi over 4. So putting pi over 4 in, pi over 4 times 2 is pi over 2. Tan of pi over 4 is 1. And put 0 into both of these, you're going to get 0 minus tan of 0 is 0. So this is our exact form. We don't need to simplify that anymore. Pi over 2 subtract 1. And we're done for part A. Part 2, we've got Alice riding on some ride that's got teacups going around a teapot. Some sort of Alice in Wonderland type fantasy. We're told the x coordinate and the y coordinate in terms of theta, the angle that the center of the cup is from the center of the ride. And so 5 spinning teacups that rotate on circular sources, a circular platform that rotates around a large teapot at its center. The coordinates of Alice's motion can be described by these parametric equations, where theta is the anti-clockwise angle as shown. Find the coordinates in the first quadrant. So we're just looking in this quadrant here, where Alice is closest to the teapot. Justify your answer. So closest, this is the distance. Well, we've got one outside the quadrant, but this is Alice, and her distance to the teapot is here, but the distance to the center of the teapot is just the same distance, but with a radius added to it. So we can note to start with that the distance to teapot is the same as the distance to the origin, subtract the radius of the teapot. And moreover, this radius to the teapot is constant. So if we minimize the distance to the origin, we will automatically minimize the distance to the teapot. So I think that's an easier thing to do. So that's one note. The second note, so that means now we want to minimize the square root, x squared plus y squared. This is the distance from the origin, so we want to minimize that, but we can achieve that by minimizing the square of that distance. Distances are positive. If we square something positive, we get another positive number, but square root is a strictly increasing function, so squaring it, we still get something that's strictly increasing as we go further away from the origin. And the minimum of the square of the distance is going to occur at exactly the same point as the minimum of the distance. And that will save our algebra, so we can minimize we can minimize x squared plus y squared. I think that will make our algebra a little easier. It gets a bit messy as it is, but so let's just calculate these things. Let's call x squared plus y squared, just call it something, call it f. So we have f is equal to x squared plus y squared, and that's 4 times the cosine of theta plus the cosine of 4 theta, all squared, plus 4 times the sine of theta plus the sine of 4 theta, also all squared. Square those brackets. 4 4s are 16 cos squared theta plus the mixed term is going to be 4 times 1 is 4, 2 of those, so you get 8 cos theta cos 4 theta, and then we get the cosine squared of 4 theta, and then add on the square of the y term that involves sines and not cosines, otherwise it's identical. So we're basically just copying down, replacing cosine with sine. And then remember that cosine plus sine, cosine squared plus sine squared, whatever the angle, is 1. So we've got 16 times 1 here, and we got 1 over here. So this is equal to 17 plus 8 lots of cos theta cos 4 theta plus sine theta sine 4 theta. Just going to move the second part of the question, give us a bit more working space. Might have to move it back later. We can do some simplification with this here. It's in your formula sheet, but it's interesting to see it derived. If you have cos A plus B, that's equal to cos A cos B. Take off sine A sine B. And these terms that we've got are like cos A cos B and sine A sine B. So that it will, something from here will help us simplify this. Similarly, if you worked out cos A minus B, you'd get cos A cos of minus B, and then minus sine A sine of minus B. And because of the symmetry in the cosine graph and the sine graph, cos of negative B, that's just the cosine graph is a reflection in the y-axis. And just goes back the other way. Excuse my poor drawing. And this is cosine. And sine is a rotation. So when you negate the angle, then you negate the sine, which will make this become plus sine A sine B. Now I probably shouldn't have drawn pictures over there, but we'll make do. If we add these two equations, what happens is the sine terms are going to vanish because one's got a minus sign, one's got a plus sign. So we get cosine A plus B plus cosine A minus B is equal to, these ones double up, 2 cosine A cosine B. And that's basically what we've got here. we've got a cosine A, cosine B term, so we can split that into the cosine of the sum and the cosine of the difference of the terms. And if we subtract, then it's these ones that we'll lose because they're the same. So we subtract, it's perhaps easier to take this one and subtract the top one. So let's write them in the opposite order. Cosine A minus B subtract cosine A plus B is equal to this, subtract that, so it would be 2 sine A sine B. So we're going to use those formulas. You can look them up on your formula sheet as I said. So back to our working proper, we've got 17 plus 8. I'll leave that out. Cos theta, cos 4 theta, that's this one. So that's going to be half of this. So it's the sum of the cosine of the sum, so cosine of 5 theta, and the cosine of the difference, A and B, we can write these in either order. So put the biggest one first will do for us. So plus cosine 3 theta over 2, and sine, again we can change the order here. So when we do the subtraction, we'll do 4 minus 1. So sine is going to be the difference of these. So it's plus cosine 3 theta minus cosine 5 theta over 2. The minus 5 theta and the 5 theta, they cancel. So we've got 2 lots of this divided by 2, so that the 2's will cancel. So we end up with 17 plus 8 cosine 3 theta. And this is the distance, we called it f, that we wish to minimize. And basically this is just a cosine graph. It's got a shift, a vertical shift, and it's got this changes the amplitude, and this 3 changes the frequency, but it's just cosine. Shifted up 17, but so really we've got 17 up here, and we're going from 18, and we're just going around like this. The minimum of cosine 3 theta is -1. And it occurs when 3 theta equals pi. Here's a cosine graph. This minimum corresponds with the value of pi. So therefore, theta is pi over 3. It occurs at other values, but they will be outside the first quadrant. So this is the only one in the first quadrant. The question asked us to find the coordinates in the first quadrant. So to find the coordinates, we want x equal to 4 cosine pi over 3 plus cosine 4 pi over 3. Yeah, that's right. Now, I normally draw my special triangles the other way. I'm not sure what I normally do like this. This is pi over 3. This is 1. This is 2. This is root 3. Cosine pi over 3 is 1 over 2. So this is half of 4. Seem to be drawing cos graphs forever. This was pi, remember. Pi over 4 is somewhere in here. So it's the negative of the cosine of pi over 3. So this is negative 1/2, which is equal to 3 over 2. And y is for the sine of pi over 3 plus the sine of 4 pi over 3. Sine of pi over 3 is root 3 over 2, so still 2 times root 3, and plus sine graph, this is still pi in the middle here, 4 pi over 3 in here is the negative of the sine of pi over 3, so sine pi over 3 is root 3 over 2, so this is minus root 3 over 2. So 4 root 3 over 2 minus 1 root 3 over 2, it's 3 root 3 over 2, and the coordinates of the point are 3 over 2 and 3 root 3 over 2. Didn't say the exact answer here, so you could convert that to a decimal if you wanted. And I nearly got the spacing right when I shifted, so we can just go on. Find the distance Alice travels in one complete rotation around the teapot. Note, when a curve is defined parametrically by the equations x equals f of theta and y equals g of theta on an interval alpha less than theta less than beta, we can find its length by using this formula here. So we want the length, which is going to be our integral. Theta is going to range from 0 to 2 pi, and we've got this mess to calculate. I'm going to build this up piece by piece over on the right, and then we'll do the integral. So we want dx by d theta. X was 4 cosine theta, so differentiate that, you get 4 sine theta with a minus sign, plus cosine 4 theta, so you get sine 4 theta. Chain rule, you have to multiply by 4. You also get a negative sign from the differentiation, so that's dx by d theta. dy by d theta, we're differentiating 4 sine theta, which will give us 4 cosine theta, and plus sine 4 theta. Yeah, sine 4 theta, so you get cosine 4 theta. Chain rule, have to multiply by 4. No minus signs to deal with. So that's that. Next thing we need is dx by d theta squared plus dy by d theta squared. So square both of these. When you square two things with a minus sign, it's going to be the same as squaring with a plus sign, so we don't need to really worry about the minus sign. Square the first term, you get 16 sine squared theta. The mixed term is minus times minus. It's going to be a plus again. 4 4s are 16. There's 2 of those mixed terms, so it's plus 32 sine theta sine 4 theta. And then plus another 16 sine squared 4 theta. So it's very similar. Then we're adding on the same thing for this cosine expression squared, and it's going to be identical with the sines replaced by cosine. So it's 16 cosine squared theta plus there's 32 of the mixed term cosine theta cosine 4 theta plus 16 cosine squared 4 theta. And just as in the previous part, these cosine squared plus sine squared terms add to 1, so we get 16 here and another 16 over here, so that gives us 32. There's also 32 in front here, and then we have sine theta, sine 4 theta, plus cosine theta, cosine 4 theta. And that's identical, isn't it, to what we've already calculated up here. Sine theta, sine 4 theta, cosine theta, cos 4 theta, adding those together. So when you add them together, you end up with just cosine 3 theta. So we can write this as 32 plus 32 cosine 3 theta. And that would be a perfectly acceptable expression, but it's not that helpful at the moment because we have to take the square root of that, and it doesn't look like it's got a nice square root. But there is a little trick that we can do, and the trick we can do is using the same it's from the previous question. It's the cosine 2x. So you can change a cosine of a double angle into something that involves cosines and sines, or cosines minus 1. So how we use that trick here is that we rewrite this as 32 plus 32 cosine. We want a 2. We don't have a 2. We just put it in and halve the angle. So 2 lots of half this. And then this is 32 plus 32 cosine double angle. You can rewrite that as 2 cosine squared of half the angle, and then minus 1. And that little trick, it introduces a square, which will help us when we take a square root. And this minus 1 is very convenient because 32 times minus 1 is going to cancel exactly with the 32 here. So now we just have 32 times 2, which is 64. That's convenient as well, as it's a perfect square. Cosine squared of 3 theta over 2. And there's one other, before we put it into the integration, there's one other little tricky and important thing, which is often, unfortunately, in some of the NCA examinations overlooked by the examiners. We want to take the square root of this. That's the square root of 64 cosine squared 3 theta over 2. Square root of 64 is easy, that's 8. And we're often lulled into writing down cosine 3 theta over 2, but this isn't quite correct, because a square root here implicitly means the positive square root. So we don't write it in, but it's implicit that this is the positive square root. Cosine, on the other hand, depending on the angle, can be negative. Therefore, when we do this step here, we need to put absolute value signs around this. Basically, side note to my side note, the square root of x squared is not equal to x. The square root of x squared is equal to the absolute value of x. If x is negative, you have to get a positive answer, and x will be negative, so these two things are not the same. So now we're in a position to at least start the integral. a lot of work to get there. We've got 8 absolute value cosine 3 theta over 2 d theta. Now this cosine graph's periodic and it's got a lot of symmetry to it. So we're going from, what do? Let's do 3 of these for pi and 2 pi. We're going, theta's coming out to here. When theta is 2 pi, we get the cosine, the 2's are going to cancel, it's going to be the cosine of 3 pi. So the cosine of 3 pi is back here. Yeah. When theta equals pi, we get the cosine of 3 pi over 2, which normally cosine graph goes like this. 3 pi over 2 would be here, so we get back to a cross of 0. So we start up, I think our normal period is going to be pi over 3 no, not thinking straight there. Effectively, this is basically 1.5 periods of a normal cosine graph. So we're going to go up, down. Where are we going through? It's going to finish down here, isn't it? Yeah, cosine of 3 pi, I said it was here. That's what I confused. Cosine of 3 pi is the same as cosine of pi normally, which is down at -1. So we've got a graph that goes like, it's got its minimum. Excuse my bad drawing. My maths lecturer used to say when he drew bad drawings, this would give him an E in fine arts. We need to go up to 2, that would help a little bit. But basically this area, these 2 areas, and this final area are all the same. And so this integral is actually the same as an integral from, instead of 0 to pi over 3, it's 0 to pi, 2 pi, it's 0 to pi over 3, and there's 6 of them. So we can change our integral, take the 8 outside, multiply by 6, so 6 times 8, the integral from 0 to pi over 3. We can drop the absolute value because in the range 0 to pi over 3, cosine is always positive. Then we get 48. Integrate cosine, you get sine. Divide by the 3 over 2, same as multiplying by 2 over 3. And evaluate at pi over 3 and 0. 48 over 3 is 16, times 2 is 32. Sine of pi over 3 times 3 over 2, the 3's cancel, so it's sine of pi over 2. Sine of pi over 2 is this value up here, it's 1. So this is 1 minus 0. So final answer, you get 32. That is the total distance. Presumably that's in meters. Yeah. Move on to another fun question. This is a Pythagorean theorem proof that was discovered by 2 school girls in the United States. in 2023. It's quite remarkable because it is a trigonometric proof, and it was sort of thought that there were no trigonometric proofs, but it's a little unclear exactly what that means, and there are some other proofs that are trigonometric, but nevertheless it's a novel proof, and these girls found more than one proof, so quite remarkable that they did this, and this was one of the girls' proofs that was presented. I think the American Mathematical Society or something like that. So this question basically walks us through that proof, or guides us through that proof, and we need to follow and see the reasoning. So the girls made this this triangle, which they called a waffle, I think, waffle cone, yeah. And it's made up of these an infinite set of similar triangles. The triangles are similar because the angles have to be all the same, and they are decreasing in dimensions, so they're getting smaller and smaller and smaller. So there's an infinite number of these as you go down, and based on that triangle, they were able to get two expressions, as we will see in a minute, for the sine of this double angle up here. And the two expressions were only going to be consistent if a squared plus b squared equals c squared, the well-known Pythagorean theorem. So let's walk through and see how they do that. So first part of this says show that c squared equals 2ab over sine 2 alpha. I think, given that sine 2 alpha appears in there, I think we could start off by looking at what sine 2 alpha is. And we have a formula for this. This is 2 times the sine of alpha multiplied by the cosine of alpha. And in the question, we've got a simple right angle triangle here. So if we look at this right angle triangle, probably my diagram is going to get messy. So we're looking at this one at the moment. So in that triangle, sine of alpha, opposite is a over hypotenuse. And the cosine of alpha, adjacent is b over the hypotenuse. And so that means that our expression above, sine 2 alpha, is equal to 2 times a over c multiplied by b over c. And I think you can see pretty quickly, if we multiply up by the two c's, we will get c squared over on the left-hand side. We're left with 2ab on the right-hand side, and if we divide through by the sine 2 alpha, we get the expression that's required in the question. I did think of an alternative way of doing that, and that is, as I said, this is going to get messy. If we use a big, let's rub off. We rub this off. If we consider the big triangle at the top, we can use the sine rule on that. So alternative, the sine rule tells us that sine of 2 alpha divided by 2a, that's the length opposite, is equal to the sine of beta, its angle opposite is c. And sine of beta's down here, that's b over c. So this is b over c divided by c, which is b over c squared. And then just cross multiplying again. C squared we multiply up onto the left hand side, 2a we multiply up onto the right hand side, divide by the sine 2 alpha on the right hand side. So there's two quite simple proofs of what we're required to show there. One using the double angle formula for sine, and one using the sine sine rule. So this is a sine. Let's look at the next part. Yep, can move that up. I run out a bit of screen real estate here, but we've got a length u of this big waffle that is made up of these similar triangles, and it's asking us to show that u equals some expression here. And what u is, if I call this side u1, this side u2, this side u3, dot, 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 we've got that u is the sum of these ui's. There's infinitely many of them. So we sum from 1 to infinity. That says us also find a similar expression for v. So v is slightly different because v is made up of these ones here, which I'll call v1, v2, v3, etc. And this first one we could call v0, but it's c. v0 is exactly equal to c, so that's why I'm not starting with that one, because it's got a slightly different format. So we could write that as c plus the sum of the vi's, I equals 1 to infinity. Yeah. Let's have a look at these the lengths of these sides, these ui's to start with. We almost do them both together though, as it happens. But these triangles, as I noted before, are similar because this angle's alpha, this angle's beta, and we've got a right angle. Up here we've got an alpha, a beta, and a right angle. So our longest of our two non-hypotenuse sides here is 2a, and over up here it's b. So to get from this triangle to this one, we multiply by, we start with b and we want to get to 2a. We multiply by 2a and divided by b to get this length here. So we're starting with b. There's obviously a scale factor. So to get to 2a, we have to multiply by 2, we have to multiply by a, and we have to divide by b. And that means that this shorter side, which starts off as a here, has to have the same multiplicative scale factor. So it was a, we multiply by 2a over b, so we get 2a squared over b is this side here. And similarly, the hypotenuse, which is what we wanted, is c multiplied by 2a over b. So it's u1, let's write it down the bottom. That's what we're going to add up. u1 is 2ac divided by b. So we're going from this small triangle at the top to this bigger triangle below, and we looked at the ratio of the sides. We've only got one side known of that bigger one, so we have to find the corresponding side on the smaller triangle, which was this B. And we can, because they're similar triangles, they must be multiplied by the same constant factor, scale factor. And we found that the scale factor is 2a over b, so this is the scale factor. And then we can keep on doing this because we now have a triangle here and then this triangle over here, which makes up the V1 side, or includes the V1 side. We can look at the scale factors there as well, because the shorter side on the big triangle here becomes the longer side. So to get from here to here, the scale factor is A over B. So that means the shorter side is going to be this side multiplied by A over B. So it'll be 2a cubed over b squared. The hypotenuse will be this thing here multiplied by a over b. So this V1 is 2a squared c over b squared. It's taking the u1 and multiplying it by that. And we get, so we got a scale factor here of, from here to here, we get a scale factor of, so from this triangle to this triangle, scale factor is a over b. But then we see the same thing here, because we got 2a squared over b, and we get to 2a cubed over b squared. The scale factor here is also from this triangle to this one. The scale factor is also a over b, and that's going to be the same all the way down. So that means, in turn, that the scale factor from this triangle to this triangle, we've got this intermediate step. The scale factor is a squared over b squared. And so that will tell us that u2 is 2a cubed over c over b cubed. u3 is 2a to the 5 over b to the power of 5, etc. Dot, dot, dot. Then u, remember, is the sum of all these things. And the hint is basically telling us about the sums of these things. This is a finite sum, but the general form for an infinite sum of a geometric sequence is the first term divided by 1 minus the ratio. That's the sum to infinity. And you can see that because we want the ratio to be less than 1, absolute value of it. So if we raise something that's less than 1 to a big power, this term just drops off. This is going to 0. So we've got the 1 over t minus 1 over 1 minus r, where t1 is the first term. So I've used a as the first term here. So that means over here that u is 2ac over b, and then divided by 1 minus, and we found our scale factor was a squared over b squared between each second one of these triangles. I'm going to multiply this by b squared over b squared. It'll get rid of the fractions in both the numerator and the denominator. Cancel, one of them will cancel on the top, so we get 2abc, and on the bottom we're going to get b squared minus a squared, and that's exactly what we want in the question. A similar expression for v remember we said was C plus V1 we found is 2a squared C over B squared, 2a squared C over B squared. The scale factor was exactly the same, so the next one is going to be 2a to the 4 C over B to the 4 plus 2a to the 6 C over B to the 6 plus ... We've got a C at the front. This is an infinite geometric sequence, scale factor or common ratio a squared over b squared. So this is going to be 2a squared C over b squared divided by 1 minus a squared over b squared. Same trick, multiply by b squared over b squared to get rid of the fractions in the numerator and the denominator. We get C plus 2a squared C over b squared minus a squared. Put all this on a common denominator, so this becomes C times b squared minus a squared plus 2a squared C over b squared minus a squared. We've got C times b squared, and then C times a squared, a minus sign here, but plus 2 more of them, so it's going to change it to a plus sign. So we get C a squared plus b squared over b squared minus a squared. So that's our similar expression for V. And then it says, hence, prove that a squared plus b squared equals c squared. Now, the way we do that is if we look at this triangle, look at this big triangle, waffle. We've got an angle of 2 alpha up here, and the sine of 2 alpha is going to be this side u divided by this side v. So finally, maybe that's a bit hard to read, but we'll go with it since I used a yellow one. The sine of 2 alpha equals u over v, which is equal to 2abc over b squared minus a squared divided by a squared plus b squared times c over b squared minus a squared. These cancel. The c cancels, so that leaves us with 2ab over a squared plus b squared. But in the first part of the question, we found that sine 2 alpha was equal to 2ab over c squared. Right up here. If these two things are the same, they've got the same numerator, the denominators have to be the same. Therefore, a squared plus b squared equals c squared. Something that Pythagoras knew thousands of years ago. So that's the end of question 3 in 2024 scholarship examination, calculus. Any questions, put them in the comments. Otherwise, I'll see you next time with question 4. Thanks for watching.